So the last time we were doing the Chinese remainder theorem. Chinese remainder. Now this turns out to be, as you guys know, this turns out to be a very, very important theorem to produce special kinds of numbers which satisfy, more than one remainder condition at the same time. So what kind of things does it solve? What is the statement? So let's mention that. Given m and n, which are co-prime, the GCD is 1. Two numbers whose GCD is 1, and a and b, and let's say you can say that a is between 0 and m, and the b is between, because these are the a is supposed to be the remainder, when something is divided by m, and this is between 0 and n. So maybe, okay. Given these things, there exists x such that x leaves a remainder a. So x leaves a remainder a when divided by m. This is the notation for that. Okay, we have said this last time, but it just means I'll just say through an example, and then we'll move forward into what more do we need to make this computable, make it, be able to find such numbers, not just know that they exist, such that x leaves a remainder a when divided by m, and x also the same x again leaves a remainder b when divided by n. This was the statement. Everybody agrees with this? Yeah. Now let me say it through an example. So this kind of problem was there in the test, and that was small numbers. So some of you were able to find it explicitly, so that's not a problem. So for example, let me put it like this: find a number that leaves a remainder that leaves a remainder 1 when divided by 12, okay, and remainder 2 when divided by 43, right? And what we have shown last time is that such a number exists. Such a number will exist, okay? So Pragdish, do you understand this statement? So just a question, right? I want to, we want to find a number x which satisfies both these properties. And so basically here you see that this is the m, and this is the n, this is your a, and this is your b. And we are saying that find the x. Now we know from the theorem discussion we had last time using pigeonhole principle that such a number will exist. But now let us try to find it today. Let's have a good efficient way to find it. So all of you try to find such a number. Then we can talk more about this. So if anyone can find it, we can. So how did you do it? Let's see that. Right. So that is the thing. How do you find the 18 and the thing? That is the right. So you got this is equal to 1. And so uh, what did you get Z as? Okay. And Y as 18. Okay. So I suppose all of us can check that this works. That's not a problem. But then, yeah, okay, no problem. This is seems to be smallest. Yeah. So, but how did you find it? Just by guessing and so on. Right, right. Right. So anyone else has got any solution? So you don't have to get the same solution, in fact. You could get something different also, but this is like the smallest in some sense. Oh yeah, I always write this wrong way. Right. Yeah, otherwise this is not even true. Makes sense. Yeah. So anyone else has found a solution? All right. Let's see. Let's wait. Yeah, let's see. And meanwhile, if you have found, then you can tell me or try to think. How do you find such solutions? In a systematic way, right? Oh no, I cannot hear you, Shana. It's too volume is too low. Yeah. Okay. So sorry, you wrote it like this. Hmm. Okay. Okay. So that's another way. Okay. Anyone else has found a solution? Okay. So for Ishana and Aparna who have found the solution, can you find quickly one more solution? One more solution. It's just good to find a few more solutions and see, compare them, because we had asked those questions last time, some related questions. No? There's a unique solution between what, and so on and so on. And everybody can obviously put this and check that it indeed works. Yeah. And we have some heuristics to find them, but no concrete method. Nobody is able to find one more solution. So you can build on this solution itself. You don't have to go searching for another solution completely separately. So the last time we saw, right, if there is if there is a solution z equal to 5 which works, then when will the next possible z come? The LCM of y and z. Sorry, say it again louder. No, I don't think that is true. I don't think that is true. You mean adding multiples of 43 into 12? Or, okay. So you're saying 5 plus 43 into 12. Like this. No? Huh. 270. Oh, sorry. So I'm just, yeah, it's because I was, okay, yeah. So this, you're getting 43 into 5 plus 2, right? But this is 217. Hmm. Yeah, next number is? Right. So you're saying the next, yeah, the next x. Okay. Is 43 into 12. Right. So Aparna, I think you were also saying the same thing. Yeah, like the, so yeah, that's right. The next x itself will be 43 into 12, because certainly this will work, right? I mean, certainly this is going to work, right? This will also leave the same remainder when divided by 43 and when divided by 12, because you've added this. And this is the next solution, right? There is no solution in between. Okay, so there is a 217 which does the job. And then after that, if you go for look for a bigger solution, the next number has to be this. Yeah, there is no number in between that can possibly work. Is that, yeah? So can we try to prove this more formally, that there is no solution in between these two numbers? There is no possible x. I wanted to understand z and y, but that's okay. We are trying to understand x now, but I said solution, so yeah. Anyways, so how do we say that between 217 and 217 plus 43 times 12, there is no other solution, no other x which does the job? So yeah, is the question to everyone? So x equal to 12y plus 1 is a solution. So x equal to 217 is a solution. And then x equal to 270 plus 43 into 12 is a solution. We want to say that nothing in between is a solution. Means nothing in between, satisfies those remainder properties. But is that completely convincing? Because yeah, so you should, yeah, that's right. But then but one has to still put it more formally, right? Is it needed? So my question is, so basically, if 217 plus t, yeah, leaves remainder 1 divided by 12 and so on, then why should t be 43 into 12 times something? Right, that is what. And so then it's easy to, it's not hard, I mean it's easy, because I mean 217, so what remainder will 217 plus t leave when divided by 12? Yeah, so 217 plus t is equal to, so we already know that 217 leaves the remainder 1, right? So that is 12 times something quotient, which is not important. That's already, that's why we know the y. So let's write it. 18 plus 1 plus t, and this leaves the remainder 1 when divided by 12. Yeah, this leaves the remainder 1 when divided by 12, which means that this minus 1 should be divisible by 12. One can say it like that. Yeah, which basically means that t should be divisible by 12. Yeah, 12 should divide t. Okay, and similarly 43 should also divide t. When you do the reasoning there, then from there you can say that, I mean, yes, it's a correct. I mean, the answer and explanation is okay, but this is just following more from the rules. Okay. All right. So well, basically, this we already have seen last time in another way we kind of said it last time, but today we have kind of understood it in this other way, right? That given any x that you're looking for such an x, yeah, such an x will exist, but we are now able to say that there will be a unique x. Okay, so we'll come to the point of finding them in a more systematic way, but at least we can say that there exists an x, and moreover, uh, between 0 to between 0 to maybe whatever I can, between 0 to mn minus 1, or 1 to mn, yeah, there is a unique x. Yeah, there is only one such x, okay, between the one and the product, right? Okay, last time we had seen this in a more conceptual way, right? Or rather, maybe it's like if you had, let's say, 4 and 17, right? Yeah, then what did we say? That if you take any number here, x, and you send this to remainder when divided by 4 and remainder when divided by 17, right? So for example, if you take 47, then where will this go? 3 comma. Yeah. 14 or 13. 13. Yeah. Everybody understands this, right? It's like the reverse thing. Okay. So I'm just stressing on this because this is going to be important later on. There is, yeah. But the point is that we said that, so given any number, you can look at its remainder when divided by 4, and you can write that in the first, coordinate. And then you can look at the remainder release when divided by 13, sorry, 17, and you can put it in the second coordinate. Okay. And basically, we are saying that you can also go reverse, because for any a comma b, you can find such an x, right? That is what that's what we have said. That's what this theorem says. But then today and even last day, we saw it in a slightly different way. Yeah, but that's okay. Let's not go there again. Point is that we understand that given any a comma b here, it comes from how many different x's? Unique x, right? If you are sticking this thing from 1 to 4 times 17, or 0 to that, the same thing. If you're sticking here from 1 to 4 times 17, yeah, all the way dot till 4 times 17, yeah, then there is a unique for every x. For everything on the left hand side, there is a unique thing on the right hand side. That's obvious. But everything on the right hand side, there is something on the left hand side. That's what we have said, right? For any two remainders, there is a number, but there is a unique number. Okay, so this is the bijection. There is a correspondence. We have matched the elements on both sides. Okay, and also the size of the two sets is same, right? Both sides is 4 times 17. Is it fine? Huh? So like just now we saw something, right? Just now we saw that if you have 1 and 2, then where does it come from? Or we didn't see that. So if in this case, can anybody tell where does 1 comma 2 come from? So try to calculate. Again, you can just frame it in terms of remainders. That's what it is, right? And say where it comes from. $53, yeah, and that's correct, right? 53. Yeah, 53. Yeah, because 17 times 3 is 51, and so 53 leaves remainder 2. Right. So this is correct, right? So you can see for every pair on the right hand side, you get something. So in that sense, it's like a just question, combinatorial question. All right. It is nice, a nice bijection. But there is more to this. There is more to this. Okay. See what I mean. If you think about the, so we'll come to the computation, but let us just think, right? If I'm taking the numbers from 1 to 4 times 17, okay? But if I take, for example, the number 47, and 47 leads me to 3 comma 13, if I just extend for a second, if I extend for a second and I consider 47 plus 4 into 17, do you think that is this any different from 47? Exactly, right? Up till the remainder factors, I mean, up till, as long as we are only interested in the remainders, yeah, as long as we are only interested in the remainders, 47 plus 4 times 17 is the same as 47. Okay, there is a difference. I mean, there is a difference But if you are only interested in remainders when divided by 4 and 17, not just by 4, but 4 and 17 both, okay, equally. In that case, these two numbers, 47 and 47 plus 4 times 17, are the same things. Okay. Because this will, I mean, if we consider remainder strictly, this will obviously go again to the same thing, right? So that is why on the left-hand side, we are only considering numbers from 1 to 4 times 17, not more than that, okay? But if somehow we end up going forward, we can just subtract some 4 times 17 and we can come inside, okay? Right? So basically I'm saying that you take anything, when you do addition here in this set, if you get a number more than 4 times 17, then just subtract 4 times 17. Okay. Right. Yeah. So I am putting a kind of addition. I'm putting a kind of addition here. So addition, just a second. Addition in this set, yeah, is done. Modulo, this is what it's called. Modulo is also a word that we use in common life, right? I mean, yeah, I mean, I could have, I mean, I did this modulo this fact, right? Modulo this fact, I got this, yeah, or whatever. Right? So I mean, like if you don't consider that, then I won, or if you don't consider that, then I went there or whatever. Right? I reached, yeah. So modulo means not considering 4 times 17, yeah, or considering 4 times 17 as 0. Addition in this is done modulo 4 times 17. Right? And similarly, if you are in this particular coordinate, then you see addition is done modulo 4. Right? I mean, 5 is the same as 1. Right? 6 is the same as 2. Okay? But that's all this roughly. You don't, one doesn't need to, so one can introduce these things formally, but not doing it now. Because all I want you guys to see is the following. Okay? Yeah. So we know that 47 is matched to 3, 13, and you know that 53 is matched to 1, 2. Okay. So can anybody tell me what is 4, 15 matched with? Yes. So the 4 is 0, right? So the 4 you can consider as 0, right? So 4 is same as 0. You can write a 4 or you can write a 0. Yeah, it's the same thing. But yeah, I should write 0. $32. So how did you find 32? Right. Okay, that's okay. Now, so but you guys see that the 0, 15 I have written is strategic. I mean, it has a certain pattern with the other two things. You see? Yeah. So it's 3 plus 1, that is 0 here. And this is 13 plus 2, that is 15 here. Now, can you check this side also if it's the same thing? You see, 47 plus 53 is 100. And 100 is this, I mean, so 100 and then 100 is more than 17 times 4. So if you subtract 17 times 4, then you can check that it is 32. Yeah. So do you guys see that? So you see what is happening, right? So there is more than just, there's a lot more happening here than just bijection, right? Even the numbers adding on the left hand side and the remainders adding on the right hand side is working out. Okay, so this is beautiful. It means that not just that these two sets are in bijection, but even kind of the arithmetic is there is a mirror in that also. Okay, that's all I want to say. Okay, for homework, you can check that in multiplication, when you multiply these two, like coordinate wise, 3 times 1 and 13 times 2, and you check for the x for that, and then you multiply those two there and check, you'll see they also match. You just do the same thing for multiplication and subtraction and so on. You see it just matches. So do those things for homework. Yeah, fine. So basically there is a lot going on. Okay. But how can, okay, all that is very good, but how can we use it in a to computational advantage? Well, we can, right? Because now that you know there is this additive thing going on, what does it mean? It means that all you need to find is where is 1 comma 0 coming from. So can someone tell me where is 1 comma 0 coming from? And also, okay, so that's a little luckily, right? Luckily coming from 70. Okay. And where is 0 comma 1 coming from? But it's right, it's coming from 17. It's coming from 52. Indeed, right? So can you guys foresee how these two could be the key to finding other things, other x's? We have not proved anything. We will do that in a more rigorous way, maybe later. But point is that now that you know these two numbers are they're very tremendous in the sense that in the very key in the sense that um, so how should I say? It's like yeah, that is, yeah, you get another one, but that's right. That is certainly correct. But what if I just ask you to find, let's say 4 comma 7? Can you do it directly from using this two? Yeah. And the answer is yes, right? You just multiply this by 4, or you just add it 4 times, right? And you just add this 7 times. And that shall be your answer to 4 comma 7. See, we don't have a proof, but that is how it is working out in what we have seen. Right. I mean, the 1 comma 0, you add 4 times to itself, right? Then you will get the thing for 4 comma 0, right? This is for 4 comma 0. So for 4 comma 0, it will be 4 into 17. No. Oh, yeah, I mean, 4 is 0, so it's fine. That's right. Yeah. And okay, so yeah, that's fine. The 4 is like that. I should write 0 here, maybe. Yeah. And then for 7, then you want the 7, and then you add 7 times this thing, 7 times 52. And then you add them. And that will give you, because when you add this to 0 comma 7, that will give you 4 comma 7. So left hand side, you will get the answer. So this will, so you can forget this thing, or no, maybe you should. 1 minute. No, so in this side, on the left hand side, you cannot forget it, because there the 4 really is 4. It's not 0. But 4 times 17 is 0, so it's fine. This is 0. Yeah. And then this thing, 7 2 is a 14, 1, 36, 64. And then you can subtract some proper thing from here, and you will get 4 comma 7. So you have to subtract 4 times 17, maybe several times, so that you get a number between 1 and 4 times 17. And there you find the answer for 4, 7. Yeah, was this clear? Did I confuse? Is it clear to everyone? Like how we are using the 1, 0 and 0, 1, it's just the solutions for those two to find all solutions. Yeah, let's do it. Let's do it in one more. So maybe since I just ask and others can just try to answer, and then from there we can see. Because I think I didn't say it too well, but anyways, we can do. So that's okay. Let me then say so quickly. So this should be very quick. So 11, I mean, so because this is just 4, so let's say 3, 15. So we can just find thing for 3, 15, some x. And then we can cross check and see if it's actually correct. 763. So 763 is a solution, right? And so what copy is it in 1 to 4, 17? So you have to subtract certain. Right, and so that's yeah. So like if you've got 763 is fine, but we need to still if you want to bring it in 1 68, yeah, 1 support into 17, then we should do that just to get the answer if we want the answer in that range. Otherwise, this is certainly correct. It does leave this, but just if you want to bring it in this interval. So what will the remainder be? That we will just divide and check. So just do it. 68. Yeah, but I'm subtracting 11, I think. Be able to subtract 11. 15, I think I'm getting something like this. Getting 15. Is it right? Or is it not right? You got, and is the remainder 15? The remainder is more important. Yeah, it is 15, right? And 15 obviously. So we got 763, a big number, but that's not a problem. We got it really quickly, right? This method is very good. And it's not just about the quickness. It says something very nice, that it's just that the solutions are not arbitrary, that they're related in a very nice way. So this 15 and 15 obviously works. I mean, one can just see, yeah, this is correct. And this is what you would have found if you did not know this method. So this is a very nice technique, right? Just from 1,0 and 0,1, you are able to find. And this technique is I've never seen this discussed. Usually there's a strange formula that is given, and some Bezout's theorem, and using that, which is the traditional way. But just exploring this exploring this view, obviously given two remainders and finding the solution, but then going the reverse way, that taking a number and looking at it modulo 4, okay, and then looking at it modulo 17, and seeing that these two are reverses of actual reverses of each other set theoretically, but then also arithmetically they are reverses of each other because addition is also mirrored. And then using that to find the solutions is the thing that we did. Okay, because 1,0, 0,1 you can always just find, right? Yeah. So now what should be the next question? Yeah. So, well, one next question can be is, well, tell me how to find one, because these two you cannot find. You have to find these two, right? You guys agree? Yeah. These two you have to find. These two cannot be given to you, right? But even that is not so easy. You have to maybe guess. But if it's a very big number, then so my question is then that what does this question reduce to, right? Given m and n, you want to find first. You want to find the x, which leaves a remainder 1 when divided by m, and it leaves a remainder 0 when divided by n. Do you guys agree? This is what we have to do first, right? That's your 1,0. And then the other way also. Right? So that's your starting point. I mean, at least the way we have done it. Yeah. The way we are going, that's the starting point. Yeah. So now we can frame this, right? So we can frame this just like we have been doing. What does this mean? Well, this means that x is equal to my plus 1, and that's equal to nz. And we are back to the good old question, right? That we need to solve this thing when m and n are coprime. So m and n are that's already given. So let me not write that. Solve in y in z comma y. And this is not such a trivial question, because you are able to guess, but if there is but let's say there is a very big number, like there is n equal to 2001 and n equal to maybe, I'm hoping these are coprime. Well, they are not coprime. Are these two numbers coprime? Are these two numbers coprime? Okay, because 2 is dividing, right? 3 is dividing. But these two hopefully are coprime. Hopefully. How do you solve this? How do you find the z and the y? Think, because see, we have to do this. There is no other way, right? Otherwise you will not, your project of finding these solutions, these x's which satisfy this will be failed. Even having this same method, if you don't know how to do this, then you cannot get started, right? I'm not saying that you have to be fast in calculations, and well, you should be fast, that's a different thing, but we need a systematic method to find this. It has many advantages, but to begin with, a systematic method to think about this. How do you find a z and a y which satisfy this? Now I've given a concrete question. Think about this. I'll just come in a minute. Okay. So anyone has any idea? Okay, so then let's remove everything and focus on this question solely. Okay, we know from our discussions earlier that such a solution exists for the such a z and y will exist because these two numbers are co-prime. But how to find a constructive which general principle doesn't tell us is the thing we need to try to understand. Okay. Sorry. So which one do you substitute? You want to replace the y. This thing. So what do you replace it by? But then what do you get when you write that? Yeah, you don't get anything wrong. You get a truth, but it's not useful. You get something true, but it's not useful. You get, yeah. Why does this kind of thing happen? And you substitute the same equation in that. Yeah, because it's not a wrong thing to do, and it's not wrong, but you don't get anything new. So yeah, we can forget about the variable things, just try to find the solutions to this. So let's think about, there's one approach already we have been using implicitly, right? And that involves number one. Let's not write that. It'll just be confusing. Well, one thing is that one thing which you can do is you can just try out the different multiples of z and y, right? You can try to put z equal to 1 and then take y equal to 1, then you can try y equal to 2, then you can try till y equal to 2001, right? And similarly you can take z equal to 2 and then again try. Is that right? Yeah, or you understand, right? Or you just take 1 plus this thing, just like some of us have done that, right, for finding the solutions, this thing, and just change the values of y and check when this becomes a multiple of 2017. You see the point, right? You go on and on, right? How far do you have to go? So you have to check till this becomes a multiple of 17. So you have to change the y. You put y equal to 1, 2, 3. How far do we have to go? Any idea? Well, I suppose you don't need to go farther in 2001, right? I mean, somewhere between that, you should get a multiple of 2001, right? The left-hand side should become a multiple of 2001. I mean, do you guys agree with that? Right? Yes, that's true. And 2001, but my point is that this method will work, but it's very inefficient. Yeah, it will work because theoretically we know that there is a solution. That's a very important fact, right? Theoretically, we know that the set z and y exist. We have seen that by pigeonhole principle earlier, but let's just assume that it exists. Once we know that, then one can exploit that. If one doesn't think too much further, then one can just try to use that naively, right? And I mean, if one is lucky, one will get it very quickly, right? Maybe at y equal to 3 or 4, you get the answer, or just y equal to 1, you get the answer, right? So I mean, that is my point, that this will work for, it works for small numbers, and it's not just about big and small, but it's about relatively big and small, right? So given this given this number and this number, you need to go, how many steps do you need to do? You need to do the number of steps which is the minimum of the two numbers. Is that right? Yeah. So this will certainly not work. Anyways, minimum of the, so I mean, one of these numbers, if, yeah, I mean, if this has a solution, one of these numbers should become a multiple of 2001, right? So you need to go up to, you need to take this 2001 steps. So your, if you want to call this an algorithm, because theoretically you're backed by the fact that it exists, so your algorithm will terminate, right? And then this is your naive algorithm. So it will take the minimum of the number of steps of, the number of steps will be minimum of the two numbers given, which is well, not too bad. It's fine. It's okay. Yeah, if the numbers are big, then it will take big time. That's not a, yeah. But can we do better is the question. Yeah, it's not about like good or bad means what. If there is something better, then there is a better. But otherwise, this is okay, right? So can we do better is the question. On average. I mean, sometimes this may be the best. Sometimes why you got a 2 or 3 may work and then that's best, right? But in general, can we do better? And that is the question. Yeah. So not that we don't have a method, we have a method, and it's okay if you're given numbers like 12 and 15, and which is fine. Then you can exploit these ideas. There are several ideas we have to combine, right? And to solve this, and this itself has many applications. But then using this, you get those solutions for the specific pairs of remainders, and using them you can build up to all remainders. Yeah, all that just comes naturally. You don't have to try to recall it. Take some example and try to work it out, and when you get stuck, then you try to see. But yeah, the real question is, can we do better? And the answer is yes. And the method is, yeah, and the method is very simple actually. So all of you know how to find the GCD of numbers. Maybe I should keep that. Yeah. The method lies in finding the GCD of two numbers using the long division method. So you guys, some of you will remember long time back at least, or some of you would have learned it recently. There is a long division method, right? A mysterious long division method to find GCD. Yeah, and it's a little mysterious if you don't know why it works, because GCD is defined as greatest common divisor, but suddenly you do division and remainders, so somehow you get the GCD. Okay, but let's assume it works. Maybe we'll see why it works also. Along the way, we'll have to see maybe. But that's all we will try to use. Or let's say that we are going to use that philosophy. Okay. So I mean, so if you say that, then what does it mean? um, right. So the numbers are these two numbers, and then we are going to, yeah. So as I said, we'll just use the long division. Let me just say it like this. So I'll try to say as less from before, and we can observe more will be better, right? So long division process, just a long, we'll just execute a long division process. Let me just say that. And so on what two numbers? Well, what numbers? This 2002 and maybe 2001. On these two numbers, right? These are natural choices. We will execute. So let's begin. Let's do that. This also looks like a long process, but it's much better than the, we will see. Yeah. Let's just do this patiently first, and then, yeah. So this thing, and then you divide by 2001. So now you have to tell what's a, and we'll need both, I think. Yeah. We will need both the quotient and the remainder. So try to find. Yeah, this is not such a good number for division, but okay. I'm getting confused with how many zeros. 2. And again, it will be 9. Right? So is this correct? So you guys should do this faster than me, much faster. Okay, good. You have to be fast at there because it's very important. And yeah, so you get this. Okay, so this was the initial thing, and this is what we divided by, and these two, and we got this. So now we will. So as you know, the long division process, how it. Well, maybe I should say long division method for GCD. We will take this two and do the same thing, right? Now I think it's easier. So I mean, is this familiar? I mean, do you guys agree this is what you do when you find the GCD? Right. Okay. So I'm not trying to say that this is just a new method. It's just the same idea, but maybe we'll just see what we need to do to use it to get the solution. So now what should be the, should be 1, and this is 8, right? Yeah. All right. And now again, is this correct? Yeah. 1190. Right. That's where something was wrong, right? How did 1993 come? There's no 1993 on the board. Okay. So this, so what does the remainder? 98. Okay. So then now we should, now you guys tell what should be the thing, quotient and remainder. Yes, everybody should say. I mean, yeah, calculate and tell. This is okay. Nine zero, right? Or no, 19. 19, yeah. Okay, and so again we can continue. So now it's 98 and it's 41. So we can do 2. So this is 16. Good. So then it's 16 again. No, I mean 16 here, and then again this is how much? 9. Yeah. So you see, this will this is, I mean, example I took, it just become a little long, but fine. That's maybe better even. And then we have 9 into 1 plus 7. But I want to say that even if it looks long, it will never take 2001 steps. Okay, it will not even take half of that, even in the worst case. But those are hard things to answer now, but at least we see that it. So when you get 2, then you're good. Get 1. So this is a very familiar process. Yeah, not a non-familiar process. Okay. And you can see that, you see, the point is that I want to first show that one thing here. See, every time you're getting a remainder of like 19, sorry, a quotient. Every time you're getting a quotient of like 19 or no, even two, more than one. What does that mean? It means that your job is kind of becoming half. Right? The number is kind of becoming half of what it was. Yeah, roughly speaking. Yeah. So that is good, right? So it means that it's kind of because the number is becoming half of what it was. So if it's like if there are if you have 128, then you will take 7 steps, right? 2 times 2, 2, 2, 2, 2 multiplied. But then you see sometimes you're getting a remainder of 1. Okay. Well, but even then you see, I mean, even if you're getting a remainder of 1, um, yeah, so this is the thing that has to be explained. So yeah, when you get a remainder of 1, in that case also, you will see that at least one of the numbers is decreasing a lot, right? So you had here, you had started with 2001 comma 1903, but in the next step, one of the numbers, okay, means, so um, what do I want to say here is, just a minute. Yeah, so what is happening? Let's just see let's just write the, let's just circle the pairs for a second, because I may have said something not, I mean, nothing that I'm saying is precise, but I don't want to say something misleading. So well, initially you start with this and this, right? And then you look at these pairs. So one of the pair remains the same, but the other pair decreases, right? And no, so I'm just trying to, so my goal is to try to explain that this process will not take too many steps. Okay, and I don't know if I'll be successful because the usual way is a little more complicated. But well, if I understand it, I should be able to explain it properly. And then you see again, the pair of numbers that we started with, they are kind of, obviously the pairs are going down, right? One of the numbers is remaining the same, but the other number is decreasing. 1 minute. So that's all. What do I? So if I'm going to compare it with, so 2001, and in the next step, well, what I want to say is that you will not have something, you will never have something like this. You start with a comma b, and then you get something like, um, you get something like b comma b minus 1, and then you get something like b minus 1 comma b minus 2, b minus 2 comma b minus 3, and so on. I mean, those red things that are circled. What I'm trying to say is that this will never happen. Okay, if this happens, then isn't this as bad as just the earlier method by checking multiples of 2001 and or whatever, right? Taking multiples of 2002 and plus 1 and checking which of them becomes a multiple of 2001. Is it all right? Yeah. So just again, this is rough, but you can get the idea, I think. Yeah. If this decreases like this, then it will take 2001 steps. Then this process is no good. But can it decrease like this? That's the question. Right? The long division process will never, if you continuously finding remainders, it will never decrease like this. So try to find an explanation as to why it cannot decrease like this. Yeah. Because, well, in the first step, you could have like, okay, A, B, and well, you could have that the remainder is B minus 1. No doubt that can happen in the first step. In your first go, that can happen, right? But then, so then why cannot it happen again? If I take quotient, why cannot I again get remainder B minus 2? Say that again. Next time the remainder will be 1. Perfect. Yeah. So that's basically, yeah. So Ishana, what you were saying, right? Yeah. That's the thing. Good. I was not getting this because usually we talk about these things in a different way, some recurrence and so on, and we are used to that. But this is first time I'm able to explain this, and you guys are able to help me with this. Right? Yeah, it's very simple, but you see, that's what happens. Next time the remainder is 1, remainder decreases drastically, you can say. Okay, so being good at calculations also helps you to say these things, and if not able to prove, at least say it. So you see, if it decreases by B minus 1 once, so I mean, if this decreases by 1, but the next step it decreases by a lot. And so you can never, so this time it will just, this time the process just stops completely. Okay, now you guys, it is it feels very good. At least to me it looks very good that we are able to very, without any language, able to explain that this long division process will always take less number of steps than your usual if you did this usual multiplication thing. Yeah, or it will always take much less number of steps than 2001. Yeah, that is the point, much less. And that how much less, that also we can, but that we cannot do now. We will not go into that. It will, but for if you want, you can read, there's a Wikipedia article on this, but there are other references. But anyways, let's not get into that. Usually it will not, I mean, it will never, I think it will never take more than log 2 of 2001 steps. Okay, if you, yeah, but anyways, yeah, but that's, but at least we are able to explain it just, okay. Now the homework for you guys is to imagine from these sequence of equations, how can you extract a solution? Don't try to guess the solution anymore. Now your job is to, from this sequence of equations, how can you extract a solution? See, it's not such a far-fetched question now, right? Because you have 2002, you have 2001, and you have a 1. And these are not coincidental. The GCD is 1, so you will get a 1 at the end of the day. And you started with those two numbers. And now there is an equation in between that you have to travel and connect these equations somehow and get a solution. And then that method will always work. You could have replaced by this by some n and 1, and you will always be able to solve this because you will get a 1 at the end. And if you but describe this process to merge this equation somehow, do some substitutions and get a solution, not by guessing. That's the whole point. Okay, if you guess, then you will not be able to honestly do this. Maybe you understand my point. So try to, so use this to, yeah. If you don't like this too long, take some other pair of numbers so that there are 2-3 steps, and then try to use those equations to somehow, do some substitution and get a solution. Just think, just spend some time. Okay, so let's then stop here today. Okay, as I think it was a fun, ended up being an interesting class, right? So we explained a few things, and yeah. Okay, so I will maybe give some formal homeworks, but today I think I have not given anything formal too much. Just the things that you can just work out and just see, but nothing really, nothing formal. So, and I don't want to give practice now. So 1 minute. So let me, yeah, nothing really formal today. Meaning no formal exercises. Okay. Yeah. Uh-huh. Huh. In a general situation. Yes, like this. You want to find the 1 and the 0. Sorry, I mean, you want to find the x which leaves a remainder of 1 when divided by one of the numbers and 0 by the other number. And then similarly, you want to find the x for 0, comma 1, right? And that question led us to those equations that we finally saw. For no, 4 and 17, if you multiply, no, 4 and 17 will, no, that you, no, that will, yeah. So, no, but you will get 1, comma 1, but you will not get, uh, good. Okay. That's nice. Yeah. So you're saying that you find 1, comma 0, then you can find 0, comma 1 from there. Ah, no. From 1, comma 1, you cannot find 1, comma 0. So okay, 1 minute. So 1, comma 1 is so that, yeah, that's that's a very important point, I suppose, and that's a fundamental thing here. That the 1, comma 1 actually always comes from 1. There's no doubt about that, right? This just comes from 1. Yeah. Sorry, yeah. So 4 into 17 you can do. So you can, yeah. So you can get that. But then how will you use that to find 1, comma solution for 1, comma 0 or 0, comma 1? That doesn't seem that it's possible. Yeah. So 68 plus 1. 52. Yeah. So from 1, comma 1, you cannot get both. That is not possible, I think. Right. Because it's even informationally, right, that you need two things to begin. You need to know the solutions for two of them to find solutions for all. And at least two you need. That is, you can think, right? It seems to be like that, right? At least two solutions you need to begin with to get all. But yeah, if you know, but 1, comma 1 has a very simple solution. And then if you can find for 1, comma 0, which in this situation you have found, but in general, we want to understand how to the method. And that's what the equation will tell you. But in general, when you find for 1, comma 0, then you can use 1, comma 1 to find 0, comma 1. Right, by subtraction and so on. That's a good thing. Okay, because 1, comma 1 has a simple solution, but both you cannot find from 1, comma 1. That is not possible. I think that's not possible. Okay. Yeah. So these are the thing. But that's not a problem, right? That you can always just get. Just divide by 52 and get the remainder. Divide by 68 and get the remainder. Divide by, yeah. That's right. And so for 1, comma 0, if you find a big solution, that's okay, right? You can just divide by 68 and get. And that is not a problem. Yeah. Okay. Yeah. All right. So let's see. Maybe we'll do one more class in this, and then I can give you some references to try out. Still, if you just Google around, you will get a lot of simple things to try. But yeah, I don't want to say anything now. Okay. Okay, then. Thank you. Good night.